Hi all, this is our last video in the energy option on energy and the environment. I'm hoping this is going to be a slightly shorter one than the other energy ones have been because it is largely revision. It is global warming for chemistry people. So there's only really one or two additional points that we need to cover here. So let's get right into it by looking at the study guide. So I am going to talk about what greenhouse gases are. I'm going to talk about ocean acidification, why greenhouse gases are greenhouse, and I'm going to talk about some particulates. I did talk about mechanisms when we studied IR spectroscopy, but I'll go into more of that. I'll discuss some of the evidence we've got and some of the different greenhouse gases, how we can manage CO2 emissions and pH changes, which is here. But we also talked about ocean acidification when we discussed acid deposition in the acids and bases topic. Okay, let's continue. So this is probably a diagram that you've seen some version of before. So the incident solar radiation is in the form of UV and visible light. The reflection into, so the UV and visible light, and let me just switch to my laser pointer. The UV and visible light goes through the atmosphere and strikes the Earth, which warms it up. Some of that UV and visible light reflects straight off Earth back out into space. However, once that once the UV visible light has been absorbed by Earth, that energy is then re-radiated as infrared radiation. And there are a collection of gases. So the ones that we talk the most about are CO2 and methane, because they're the ones that humans have had some of the greatest contributions to. Sorry, just switching to my pen. Yep. So carbon dioxide and methane are where humans have had some really massive impacts. One thing that I would like to stress is that the greenhouse effect on its own is a natural process. Without water molecules and carbon dioxide molecules in our atmosphere, Earth wouldn't be habitable. It wouldn't have been warm enough throughout our history to have evolved multicellular life. So the greenhouse effect originally was a natural process, but over the last 170 years or so, we've massively increased, particularly the concentration of CO2 and methane up into the atmosphere, and that's had what can now be called as the enhanced greenhouse effect. Oh. So it is natural for there to be some degree of natural greenhouse effect. What we're doing now, however, is we're enhancing that process by putting more of, again, let me just switch to my laser, putting more of these gases up into our atmosphere. Maybe not so much water, but certainly these guys. All right. So the greenhouse gases that you need to know about for the purposes of the IB are carbon dioxide, water, and methane. Oh, just a quick note, just to save me writing so much. From now on, I'm largely going to be referring to greenhouse gases as GHGs. So carbon carbon dioxide, water, and methane are all greenhouse gases. Methane is about 30 times more powerful at trapping heat than carbon dioxide is. So when we talk about carbon dioxide concentrations in the atmosphere, yeah, that's super important, but methane is also super dangerous. So methane comes from that anaerobic respiration that I spoke about last class when we were looking at biofuels. So I don't know if I mentioned in the video, but I know I did on the Zoom call. But when organic products rot without oxygen, they get broken down into methane. And that methane has much greater global warming potential. There are some other gases that can act as greenhouse gases. So we have sulfur hexafluoride, we have hydrofluorocarbons. So remember, CFCs were the ones that did the damage to the ozone layer. HFCs also have also damage the ozone, also damage increased global warming. And there are a bunch of others, but as far as the IB cares about, it's these guys. So we talked about how molecules absorb infrared radiation. So when the IR comes in, my bonds wiggle. So it's that absorption into the bonds of IR energy. So I can get waggles where that's not a waggle, that is an asymmetric stretch. I can get, sorry, how do I represent this? You know I don't draw well. I can get my bonds moving in and out. Basically, the IR gets absorbed into the bonds and the motion of these bonds. Okay. Okay, so as you can see, I just grabbed this drawing off the previous page, but I want to talk about dipole moments for a bit. So the dipole moment is, if you study vector addition in maths, it's basically the vector addition of the force of the dipole within the molecule. So it's dependent on the magnitude of the force and the direction of the force. So when you look at this printed image up in the top right, you can see that if I add together these vectors, I end up with an overall vector, a dipole moment heading straight down here. Now, if I change, for example, looking at this middle, if I've got that asymmetrical stretch, this dipole moment will change. So this is still a plus, and minus, but because of the different lengths of those two bonds now, my dipole moment will change. In order for something to be a greenhouse gas, there has to be those dipole moments. Okay. So back in the 1840s, 1850s, there was the development of something called the Newcomen steam engine. I went and saw one when I was in Edinburgh 2 years ago now, actually just over a year ago now. And it was originally designed to pump the pump the water out of mines so that miners could operate safely. Now, Newcomen, his original design was a little bit inefficient. So this guy, James Watt, made some modifications to the new common steam engine, and what is now generally considered to be the father of the Industrial Revolution. I like talking about Newcomen though, because I don't feel the guy gets enough credit. So after the development of the steam engine, before the development of the steam engine, if you wanted to heat your home, you had fires made that were built with wood, generally speaking. Coal and peat was generally lower class because it burns dirtier in a lot of ways. So if you are burning like logs of wood on a fire, but those logs have come from trees that you've grown on your property or you've bought from somebody who's grown it on their property, it is largely carbon neutral. Yes, I know about land clearing and things like that, but if you grow a tree, cut down that tree and burn it, that is a carbon neutral process. However, once the steam engine was developed, it meant that there was an increasing number of applications that it could be put to, whether it's on railways. So basically the English, when they colonised a place, they left like railroads and syphilis behind them. Yeah, that's British colonial history in a nutshell. But what then happened, all of those carbon atoms that had been locked up in coal deposits around the world was suddenly being burnt and released into the atmosphere. So when you look at a graph of carbon concentrations in the atmosphere over the course of human history, it's basically flat, 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 and then it spikes in sort of 1860. Give me a second and I'll find a picture. Okay, so this is from the NOAA, and how we can actually measure this, because we obviously, unless the Area 51 raids were really about something, we don't actually have time machines. We can't go back to the past and sample the air. However, what we can do is take usually Antarctic ice core samples where there are bubbles of air in the ice. And those bubbles of air, how deep they are under the surface of the ice, like a tree ring, tells you how far ago they were. So the natural, quote unquote, level of atmospheric CO2, and yes, there's been variations throughout history, it stayed steady at 260 for pretty much most of human history through to when the Industrial Revolution starts kicking off. And we've seen just this near exponential growth over the past few years on just massive amounts of carbon dioxide being released into the atmosphere. Okay, so the assumption, and it's probably a correct one, I'm a science teacher, so I can't say I know anything for certain. The assumption that we are going to operate under is that the Earth is warming up, global temperatures are increasing, and they are doing so as a result of human, particularly industrial activities here on Earth. So what basically happens, remember that diagram we had at the beginning with Earth? We've got our atmosphere up here, and I realized I shouldn't have done that in green initially. Actually, that's offending me. So we have our IR active water, carbon dioxide molecules that are there naturally. So when I've got my IR and UV light coming from the sun. And because I'm 5 years old on the inside, I'm going to give my son a smiley face. I've got my sun giving off that UV and IR light. It gets through the atmosphere and gets absorbed by the earth. Then I get that long wave IR that is released. So we have these naturally occurring water and carbon dioxide molecules in the atmosphere. They wiggle and flex and waggle and do their thing. But what happens when the people on Earth start being mean to our mother and start pumping a bunch of carbon dioxide, methane, and other things in? More of that IR gets trapped. It's like putting an extra blanket on. It traps more of the heat. It isn't that there's a larger heat source to begin with. Like the sun isn't suddenly pumping out a whole bunch more energy in the last 40 years. No, it's this extra blanket we've added. It's estimated, and these are the numbers that I've most recently seen. Somebody else might have more recent numbers. But in the last 40 years, the temperature has increased by about 0.5 degrees Celsius. Now, that doesn't sound massive. It doesn't. But the issue with that is, one concept that I've been talking quite a bit with the biochem people about is something called homeostasis. Natural systems work best within very tight bounds of pH and within very tight bounds of temperatures. And if I start messing with temperatures, a whole bunch of natural systems start to have problems. Okay. Oh, there is a fantastic cartoon by XKCD. If I remember, I will put a link in the description for this video, and it actually charts out variations in temperature over history, like all the way back to like before the last ice age. It's really very excellent. So a while back, there was some US senator that stood on the floor of, I was about to call it the House of Commons, Congress, and he held a snowball in his hand and he said, if global warming's happening, how is this possible? Yeah, there's seasonal variation. Now, one of the issues that's happening with global warming is that weather is becoming more extreme. We're seeing more extreme hot spells in Australian summers, and we're seeing more extreme blizzards and snowstorms in parts of Canada and in Northern Europe. Global warming doesn't necessarily mean just getting warmer. It means that because of the way that temperature change messes with ocean currents and things like that, there are greater seasonal variations. Now, another way we can talk about seasonal variations, so Mauna Loa is in Hawaii, which is the northern hemisphere. So, as you can see here, as we go through the middle of the year, you can see that the concentration of carbon dioxide in the atmosphere decreases. So between the months of, let's call it May to, is that September? Yeah. So May, June, July, August, September. In this period here, there's that massive drop. Now, why does that happen? That is, almost started writing with my highlighter. So that is the northern summer. So when it's summer, there's a lot more plants. When you actually look at a map of the Earth, there is more land mass in the northern hemisphere than there is with us in the southern hemisphere. So in the southern hemisphere, you've basically got the bottom half of Africa, the bottom half of South America, parts of Asia and Australia. When you look at the northern hemisphere, you've got all of Europe, all of Russia, all of North America and Canada. There's a lot more land mass on the north, and where there's land mass, there's plants. So in the northern summer, the plants get exposed to nice long days of sunlight, which means that we get an increase in photosynthesis. But during winter, when those trees either drop their leaves or there's less sun, there's less photosynthesis going on. So we see this cycle kick up. Then when it starts to get warmer, my plants grow back their leaves, the photosynthesis rate increases until it starts to get cold again, and we end up, and that's why we see that seasonal variation. And you can see it in this zigzaggy line. So this is from 1960 to just before this year. Okay. So global warming has a bunch of different effects. One that we're particularly interested in as chemistry people is ocean acidification. And it's basically comes down to an equilibrium. So remember back to that topic, please, as I talk about CO2 plus H2O, sometimes forming carbonic acid. And I think I specifically gave this as an example in the equilibrium topic because I knew it would come up in acids and bases, and now here. So if I increase the concentration of carbon dioxide, this equilibrium is going to shift right and cause an increase in carbonic acid. This carbonic acid is going to and can donate those two H's to form to BH pluses. There are impacts on humans. So we're just starting to see a whole bunch of climate refugees. And it's only going to get worse. Now, these climate refugees are coming from places because global warming melts ice caps. So the sea levels rise. And that is a major problem for a lot of the Pacific Islands that are quite nearby to us, where there are places, I think Kiribati is one of the places that's particularly affected. So as the ice caps melt and sea levels rise, we're looking at some fairly major movements of people. One of the other ways it can affect is it can disrupt food supplies. If your farmers can't grow because there's not enough rain, or there's not enough cold, or there's not enough stability in the climate, that's going to really affect food supplies. It has effect on the seasons. So the seasons are getting, in a lot of places, longer and hotter, and that really disrupts animals that have seasonal patterns of behaviour. So bears going into hibernation, for example. So those are the three main effects. I'm sure you know of a bunch of other ones. So I I find ocean acidification particularly interesting because it ties in much more neatly to some of the other topics we've learned, but they're all possible effects of global warming. Okay, so there are two main ways that we can control the amount of carbon dioxide in the atmosphere. We can be preventative, or we can be reactive. So reactive are things like carbon capture and storage. So basically pulling the carbon dioxide out of the air and turning it into like calcium carbonate, like limestone. So those reactive measures, they're never going to be as effective as preventative measures. If the current lockdowns taught us anything, it's that. So preventative measures, two of the most famous preventative measures for controlling greenhouse gas emissions have been the Kyoto Protocol and the Paris Agreement. Those are two of the big international agreements that have been to limit greenhouse gas emissions by various political states, various governments. Now, as we've learned in Australia, or if you happen to be an American listening to this, just because one government makes an agreement doesn't mean the next government has to uphold that agreement. So that's one limitation of these political agreements. We can move from fossil fuels to other sources of energy. So that can be any of the types of energy we've looked at. It could be solar, it could be wind, it could be tidal, it could be any of those renewables, but it can equally be nuclear. So nuclear energy, as I discussed in that previous video, despite the fact that it's the negative effects of nuclear energy that get all of the press, me personally, 2 cents worth, I think nuclear power is something that Australia could consider because it would bring down our carbon emissions. And all in all, it is safer than coal-fired power stations, which is what we run off in Victoria. And it provides a stable baseload of power, which something like solar doesn't necessarily do for us, particularly without large-scale energy storage mechanisms. Okay. So particulates are another form of pollution. So particulates are small particles, basically. So you might have seen with the current lockdown in some parts of the world, so I'm thinking particularly of some of the industrial centres in China, there's been a massive improvement in air quality. And yes, that's partially gaseous pollutants, but it's also partially solid pollutants. So a lot of them are things called like PM and then a number. That's basically saying the particle is this many picometers in diameter. Now, there is some evidence that particulates, going back to our picture, going back to our idea of the Earth and then the atmosphere, there is some reason to believe that the particulates that I'm just drawing here in black will actually decrease the amount of energy that makes it to Earth because it'll reflect it off. However, there are enough health impacts from particulates that we don't really want them. So something that isn't terribly harmful at the macro scale could actually be super damaging on the micro scale. So let's take an example. A lump of coal is something that is safe enough for our Prime Minister to handle on the floor of the house. But it's not something that you necessarily want to break down into that tiny particulate form and have it, say, travelling on a train through your country town, which is some of what some parts of Australia are dealing with. They've got large coal trains coming through, and that's massively increasing the concentration of particulates in the atmosphere. Those populations, and again, this is just based on news articles I've read and some scientific articles, those populations are suffering increases in certain lung conditions because of their exposure to these particulates. So may decrease greenhouse effect ? Because of that clouding. It's called there's a specific word for it. I think it's the albedo effect. All right. Let's go back over what we've done. So greenhouse gases allow the passage of the UV and visible light from the sun, but absorb IR, longer wavelength radiation. There is an equilibrium between the concentration of atmospheric CO2 and aqueous carbon dioxide, and that leads to ocean acidification. We've talked about these two things, we linked them. Particulates such as smoke and dust cause global dimming. We've talked about different approaches to controlling CO2. We've discussed the sources of different greenhouse gases. We didn't really talk about relative abundances. We've then got the evidence between concentration of particularly CO2 and global warming. And we talked about how our molecules absorb IR. And we discussed those three molecules in particular. All right, that's it. Have a fantastic rest of your day, and I will see you next time. Bye.